Okay, let's just dive right into this explainer and completely dismantle how you probably think artificial intelligence works. You know, when we talk about AI, especially these incredibly powerful large language models we're all using every day, it is so easy to imagine this giant, humming supercomputer somewhere, packed with endless files that are all neatly organized into pristine digital cabinets. We just naturally assume they operate exactly like our laptops or our smartphones do, just, on a much grander scale. But today, we're popping the hood. We're going to compare human neuroplasticity directly to the inner workings of an AI model, and what we uncover is going to fundamentally change how you understand and interact with these systems from here on out.
So to kick things off, we've got to ask a really foundational question. Where does AI actually store its facts? Seriously, think about it for a second. When you ask a modern AI to explain quantum physics or to write a Python script or to name historical dates from the Roman Empire, it feels entirely natural to imagine it pinging some massive server farm. We picture it rapidly scanning a Wikipedia clone saved on a hard drive or querying a massive database to fetch the exact right answer. And honestly, it makes sense. We've been conditioned by decades of standard computing, by Google searches and file directories, to think that data simply must live in a specific place. But if we want to understand what's truly happening when a model responds to your prompt, we have to completely let go of that assumption.
Because the reality is honestly kind of shocking. There is no database. Zero. There is no filing cabinet, and there is absolutely no traditional hard drive spinning up to retrieve your answers. When you prompt an AI, it isn't looking up anything at all. In fact, it is entirely devoid of standard memory storage as you and I understand it. There is no master list of facts or a hard-coded encyclopedia hidden somewhere in the code. I mean, if you were to tear apart a language model's architecture looking for the specific file that contains the capital of France, you would literally never find it. So if the data isn't sitting in a digital box just waiting to be opened, where on earth does the information actually live?
Well, if it's not a database, we need to wrap our heads around this mind-bending concept. The knowledge is actually baked entirely into the mathematical connections themselves. This is the true architecture of long-term memory in modern artificial intelligence. The network doesn't contain information in the traditional sense. The network is the information. It's this incredibly vast web of billions, sometimes trillions of intersecting points. The concepts, the rules of grammar, the historical facts, they don't exist as discrete files. They exist as relationships distributed across this massive web. And what's absolutely fascinating is that this framework isn't based on standard computing hardware design at all. To really grasp how this works, we actually have to look away from silicon and look directly at human biology. Let's look at our own brains for a second to make sense of this. We have this incredible biological process called synaptic plasticity. Basically, it's the mechanism where the physical connections in our brains, our synapses, strengthen or weaken based on experience and repetition. Think about learning to play a chord on the guitar. The first time you try it, your fingers are clumsy, right? The neural pathway is super weak. But as you practice, those neurons fire together, and through synaptic plasticity, that specific physical pathway literally thickens and strengthens. You aren't saving a file called gchord.mp4 into a rigid folder in your brain. You are physically wiring that long-term memory right into your neural pathways. The memory itself is the connection. Now, what is genuinely wild is how closely AI mirrors this exact biological phenomenon. Inside a transformer AI model, we have what are called learned weights. These are mathematically represented as query, key, and value weights, often written out as WQ, WK, and WV. Just as a human brain strengthens a physical synapse through practice, an AI adjusts these mathematical weights during its training phase. As it reads terabytes and terabytes of text, it constantly tweaks these floating point numbers. And these weights dictate the exact mathematical strength of the connections between billions of artificial nodes. They are what determine how strongly the concept of peanut butter connects to the concept of jelly, or how a specific coding syntax links together. These learned weights encode the AI's permanent library of knowledge exactly the way human synapses do.
And that brings us to this really beautiful symmetry between human biology and artificial architecture. Think about the comparison here. Neither system is pulling files from a cabinet. Neither uses a central database to look up facts. Both systems recall information based entirely on the strength of their internal routing. For humans, it's the physical synapses forged through life experience. For AI, it's the mathematical weights forged through massive data training. It is just an incredibly elegant, distributed way to encode long-term memory, completely bypassing the need for a traditional hard drive altogether.
Okay, but having all this long-term memory baked into a network doesn't really mean much if you can't, actually use it dynamically to think, reason, and respond in real time. Just like us, AI needs a way to take that deep, static knowledge and apply it to the immediate situation at hand. So let's see the AI brain in action. Let's look at how this incredibly complex web of weights builds into the broader flow of active data processing. When data actually enters the AI system, like when you type out a prompt, it moves through a highly specific sequence. First up, it hits the context window. You can think of this as the system holding the immediate details of your current conversation. It's just keeping track of the words you just typed, so it has the context. Second, that data goes to the attention engine. Now, this is arguably the single most revolutionary part of modern AI. The attention engine filters out the noise to decide what actually matters in your prompt. It scores the relevance of every word against every other word to grasp the true context. And third, it moves through the feed-forward networks. This is where those learned weights we talked about are applied to process and refine the actual meaning. So it transitions from holding temporary info to deciding what's important and finally calculating the resulting thought.
And here is where it all clicks together perfectly. Every single step of that human cognition process has an exact digital twin in the AI architecture. It's genuinely awe-inspiring how our digital systems have essentially reinvented biological sensory processing. Think about working memory in humans. That scratch pad in your mind where you hold a phone number just long enough to dial it. That maps perfectly to the AI's context window, acting like temporary RAM. Then we have the thalamus in our brain, which is our sensory gatekeeper. It keeps you from being totally overwhelmed by every sight and sound around you by filtering what to focus on. That is exactly what the AI's attention engine does for text. And finally, human pattern recognition maps directly to the AI's feed-forward networks, where the data is pushed through those millions of learned weights to synthesize and refine the actual meaning. Viewing a transformer AI model through this biological lens, it completely changes our understanding of artificial thought. And more importantly, it changes how we should interact with it. We have to stop thinking of these models as massive filing cabinets retrieving documents. Once you understand that an AI doesn't retrieve, but actually reconstructs answers on the fly based on connection strengths, suddenly things like AI hallucinations make total sense. It's not pulling the wrong file, it's traversing a probabilistic neural pathway that led to a slightly skewed conclusion. Actually, scratch that. It's exactly like a human misremembering a detail. Knowing this fundamentally alters how we should prompt these systems. Providing really rich context in your prompt directly helps that attention engine light up the correct pathways in its massive web of weights.
So, just to bring this all together, AI is absolutely not a giant search engine. Its knowledge is mathematically baked directly into the nodes of its network. Just like human biology, experience and repetition during training dictate the ultimate connection strength, using learned weights rather than physical synapses. And its active processing directly mirrors our own neurology, moving from a working memory through a filtering thalamus and into deep pattern recognition. Ultimately, an AI model doesn't retrieve a fact from a hard drive, it utilizes its temporary RAM and attention engine to traverse mathematically strengthened connections, dynamically reconstructing an answer every single time you hit send.
Which brings us to a final, really provocative thought I want to leave you with. If AI memory is wired so fundamentally like ours, what does that actually mean for the future of learning? As our artificial creations begin to mirror our own minds so incredibly closely, transitioning from rigid databases to dynamic, synaptic-like webs, what are the actual limits of their potential? And perhaps more importantly, as we build machines that emulate human cognition this perfectly in silicon, what does it ultimately reveal about the profound, mysterious mechanics of our own human intelligence? Thank you so much for joining me on this explainer. I really hope this completely flips how you view the artificial minds we interact with every single day.